Standard injection molding operates at extremes. Molten thermoplastic is forced into a steel cavity under immense pressure, traveling at velocities designed to pack the mold. To apply a finish, whether it's a high-gloss paint or a specific texture, manufacturers historically pull the formed part from the press and send it to a secondary line. In-mold technology fundamentally collapses that entire workflow. By positioning the finish directly inside the open mold before the plastic is injected, structural forming and surface decoration happen simultaneously. But introducing a foreign substrate radically alters the established physics of the molding process. The moment molten polymer strikes this material, it triggers immediate fluid dynamic and thermodynamic shockwaves. This interaction is the literal boundary between a perfect surface or a ruined part. Bypassing the paint shop comes at a cost. You are trading the mechanical labor of secondary finishing for the requirement to master these perturbed cavity physics. The baseline technique is in-mold labeling, or IML. A pre-printed film is positioned directly inside the open mold cavity before the press closes. Polyethylene terephthalate, or PET, is the standard substrate used here because it maintains strict dimensional stability when exposed to high injection temperatures. Placing that film requires exact coordination, relying on high-speed robotic end effectors or tightly machined mechanical nests, holding the label in perfect alignment. This simulation shows the primary fluid dynamic challenge. The rapid liquid melt front risks pressing the thin film against the mold wall too early. When the plastic prematurely seals the edge, remaining ambient gas has nowhere to go, trapping directly against the film surface. This trapped gas causes a defect known as a gas mark, ruining the visual and structural integrity of the finished surface. To prevent this, engineers use complex fluid dynamic simulations to map the exact flow path. By redesigning the gate location and precisely placing vents, the flow path is altered. The trapped air is squeezed out just before the melt front seals. This exact routing also prevents structural weak points, known as weld lines, from forming near any functional features on the label. Success in IML depends on viewing the inserted film as an active, calculated obstacle in a complex fluid dynamics equation. As textures become more advanced, the process scales up to in-mold decoration, or IMD. This utilizes significantly thicker polycarbonate sheets or metaromat laminates. These thicker films introduce a severe thermodynamic complication. They act as intense, localized thermal barriers inside the mold. With IMD, the film side retains heat, while the steel cools rapidly. In microcellular foaming, this imbalance creates chaos. Gas cells migrate away from the hot film toward the cooler steel, shifting the core off-center and structurally imbalancing the cross-section. The result of this uncompensated thermal asymmetry is a part severely twisting and warping the moment it ejects from the press. A proven countermeasure is double-sided IMD. Applying films to both sides of the cavity simultaneously restores a uniform temperature field, keeping the core perfectly centered. For parts with extreme or steep geometries that make in-cavity placement impossible, manufacturers pivot to outmold decoration, or OMD. OMD relies on preforming the film externally under strict vacuum and heat, sidestepping the severe overstretching and non-uniform thinning seen on sharp corners in IMD. Moving from thin IML films to thick IMD barriers forces a profound change in discipline. The focus shifts entirely from managing fluid flow to strictly policing thermodynamics, simply to prevent the part from destroying itself as it cools. In-mold coating, or IMC, discards solid films completely. Instead, specialized liquid chemistries are automatically dispensed directly into the open mold cavity space. These systems utilize thermally curable resins, UV curable formulations, and engineered polyurethanes designed for highly specific mechanical properties. Because these liquids cure in place, IMC generates a continuous engineered protective layer that vastly outperforms the scratch and chemical resistance of standard IMD films. This diagram illustrates how the liquid coating chemically integrates with the structural resin. As the two materials cure simultaneously under pressure, they lock together, forming a single, unified solid without the need for secondary adhesives. This chemical integration enables entirely new functions. Recent engineering utilizes a specialized thermoplastic polyurethane, PHEIPU, specifically formulated as an active electrode binder. This functionality transforms the mold into a production system for functional electronics directly on the part surface. Executing this requires exacting precision in fluid metering. The injected coating must spread uniformly without impeding the primary structural resin flowing right behind it. If the curing schedules of the two liquids fall out of sync, the coating will prematurely harden and interrupt the resin flow. This causes a short-shot defect, where the structural resin halts and the mold completely fails to fill. IMC pushes the boundary of part durability and functional utility, but it demands trading the mechanical hurdles of solid films for microscopic control over chemical metering and curing synchronization. Deciding between IML, IMD, and IMC requires evaluating a strict trade-off matrix, balancing part quality against initial tooling investment. Moving from basic labeling to thick films and liquid coatings yields an exponential rise in both surface finish and functional capability. But that performance requires specialized vents, active mold heating, multi-stage clamping, and hot runner systems. The mechanical complexity of the tooling scales aggressively, and despite that massive investment in tooling, a film-based IMD part will still fail if the adhesion strength between the film and the plastic is compromised. That critical bond only forms under exact pressure profiles and strict thermal residence times. Drift outside of that narrow window and the layers delaminate. Guaranteeing that bond requires utilizing sophisticated thermodynamic adhesion models to mathematically predict the precise work of adhesion needed for the chosen polymer and film. Integrating these flow simulations, thermal models, and in-mold process sensors early in the design phase is the only way to preempt defects and protect the tooling investment. Mastering in-mold surface technology requires treating decoration as a rigorous re-engineering of the entire thermodynamic molding cycle.